Welcome back to the classroom, everyone. Before we dive into the lesson, please make sure to like this video, subscribe to our channel, and follow the account so you never miss an update. Today, we are mastering virtualization concepts. We will explore everything from the foundational hypervisor at layer 1 edge, up through virtual machines, and into virtual networks and storage. Virtualization is all about moving beyond the limitations of one physical machine tied to one operating system. By emulating physical hardware resources, we can separate the operating system from the physical machine and run multiple operating systems concurrently. While traditional setups might only achieve 10% resource utilization, a virtualized environment allows for maximum hardware utilization. This emulation is made possible by the hypervisor, which is also known as a virtual machine monitor, or VMM. The hypervisor sits directly between the physical hardware and your guest virtual machine. It dynamically allocates essential resources like the CPU, RAM, and storage. Just remember, the hypervisor still requires specific hardware drivers to function. There are two primary categories of hypervisors. Type 1 hypervisors run directly on bare metal, meaning they are installed directly onto the physical hardware. Because this bypasses the need for a host operating system, they deliver the high performance required for enterprise data center environments. Common examples include VMware ESXi and Microsoft Hyper-V. On the other hand, Type 2 hypervisors leverage an existing host operating system. They are installed as software on top of that host OSA, making them excellent for client-side virtualization and local testing. However, because they share system resources with the host OS, they do introduce some resource overhead. Examples of this type include Oracle VirtualBox and VMware Workstation. Virtualization is an incredible tool for isolating threats and testing safely. Through sandboxing, you can isolate and analyze malware safely within a sealed sandbox environment that leaves the host system completely undisturbed. It is also ideal for test development, allowing you to create crash test environments where you can instantly discard any changes once the session ends. Another major advantage is keeping legacy software alive and performing cross-testing. With legacy OS support, you can run critical older applications on modern, faster hardware. Cross-platform virtualization also gives developers the power to test software across multiple different operating systems seamlessly. When it is time to allocate compute power and system memory, we depend on hardware-assisted CPU extensions like Intel, VTX, and AMD V. We also use SLAT, known as EPT for Intel and RVI for AMD, for highly efficient translation. When looking at RAM allocation, you have to ensure that the guest OS memory demands can be met beyond what the host requires. Next, we look at networking and storing the virtual infrastructure. For storage, we typically use dynamically expanding disk image files. We can also utilize snapshots to capture the exact frozen state of a VM at a specific point in time, such as a backup taken right at 10:42 a.m. On the networking side, virtual switches act as the bridge connecting VMs to the host and external networks. Security is critical here, especially defending against VM escapes and rogue sprawl. A VM escape is a severe vulnerability where malware breaks out of a guest machine to attack the hypervisor directly. You must also monitor for rogue VMs, which are unauthorized and unpatched virtual machines. Finally, avoid VM sprawl, which is the uncontrolled deployment of machines that slowly drains host resources. We can also use these concepts for centralizing computing power using virtual desktop infrastructure, or VDI. This often involves thin clients, which are low-spec devices that rely entirely on centralized servers for processing power. Remote desktop protocols are then used to transfer the screen, keyboard, and mouse inputs across the network. Moving past traditional VMs, containers offer lightweight, OS-level virtualization. Instead of emulating hardware, they share the host operating system kernel. This makes them hypervisor-free since there is no need to emulate full hardware. A container simply encapsulates specific application processes and libraries, just like you see with Docker. When choosing between full VMs and agile containers, it is important to know their core differences. Virtual machines offer maximum isolation and run completely different operating systems, but they are resource heavy. Containers are built for maximum speed. They share the underlying OS, making them extremely lightweight and highly portable. That brings our Objective 4.1 mastery to a close. We reviewed hypervisors, distinguishing between Type 1 bare metal and Type 2 hosts. We looked at VM purposes like sandboxing and legacy testing, and discussed critical resource requirements including VTX, security, switches, and snapshots. We then finished up with desktop virtualization using VDI and thin clients, alongside OS level containers like Docker. You should now be ready to crush the virtualization domain on the CompTIA A Core 1 exam. To make sure this knowledge is completely locked in, I recommend getting some hands-on practice with PBQ-like questions at XP Boost. The link is right down in the YouTube video description. Thanks for watching, and I'll see you in the next one.